Ancient DNA from 3,000-year-old bones has settled a 200-year argument and revealed the real origin of the greatest seafaring people in history. Between 800 and 1350 AD, Polynesian navigators crossed thousands of kilometers of open ocean in double-hulled canoes, colonizing one-third of the planet. Yet for centuries, no one could agree where they came from, or explain why a South American crop kept appearing across their islands. For generations, the question of Polynesian origins divided scientists into rival camps, each armed with its own clues but lacking a final answer. On one side stood the East Asian model, often called out of Taiwan. Linguists mapped a trail of sound changes, subtle shifts in consonants and vowels that connect Polynesian languages to those spoken on Taiwan and in the northern Philippines. Words for canoe, yam, and star echo across thousands of kilometers, their roots unmistakable. Archaeologists trace the Lapita pottery tradition with its intricate dentate patterns from the Bismarck archipelago to Tonga and Samoa, placing these sites at around 2,800 years before present. This view saw the first Pacific voyagers as Austronesian-speaking pioneers, sailing outward in double-hulled canoes, carrying with them crops, animals, and a shared language family. But a second school challenged this direct route. The Melanesian mixing model argued that the first settlers of remote Oceania must have blended with the Papuan peoples of New Guinea and the Solomons as they moved east. Supporters pointed to the physical diversity among islanders and the presence of Melanesian-style tools and artifacts along the migration corridor. They asked, how could voyagers cross such distances without absorbing the genes and cultures of those already living on the Stepping Stone Islands? Both camps found evidence and counter-evidence. The Lapita Trail seemed to leapfrog over Melanesian territory, yet modern Polynesians showed a complex genetic profile. Linguistics tied the languages to Asia, but the archaeological record left room for ambiguity. Then came the sweet potato, an unmistakably South American crop, long cultivated across Polynesia, its presence hinting at contact or even migration from another continent. The scene was set for a scientific standoff, with each side waiting for the breakthrough that would tip the balance. In 1947, Thor Heyerdahl set out to rewrite the story of the Pacific. With 5 companions and a raft built from balsa logs, he launched the Kon-Tiki from the coast of Peru, aiming for the distant Tuamotu archipelago. For 101 days, the raft drifted westward, carried by currents and trade winds, until it finally grounded on a coral reef more than 4,000 kilometers from where it began. Heyerdahl's message was simple and electrifying. If a handful of men could cross the Pacific on a primitive raft, so too could ancient South Americans. His book became a global bestseller, the expedition's film won an Academy Award, and the Kon-Tiki itself became a national treasure in Norway. School children reenacted the journey in playgrounds, and the idea that Polynesia might have been settled from the Americas took hold in the public imagination. But beneath the spectacle, cracks appeared. Linguists found no trace of Andean languages in Polynesia. Archaeologists pointed out the absence of South American artifacts in the earliest island settlements. The Lapita pottery trail, with its intricate designs, ran from the Bismarck archipelago to Samoa, not from the Andes. Yet, the power of Heyerdahl's narrative was hard to shake. The image of a lone raft braving the world's largest ocean left a mark on textbooks and tourism brochures for decades. The Kon-Tiki voyage didn't just offer a new theory, it blurred the line between scientific experiment and cultural myth, raising the stakes for any future evidence. If the truth about Polynesian origins was to be found, it would have to stand up not only to scholarly scrutiny, but to a legend that had captured the world's imagination. In 2016, a turning point arrived in the search for Polynesian origins. Pontus Skoglund and his team, working in ultra-clean labs, drilled into the dense petrous bone of 4 ancient Lapita skeletons, 2 from Vanuatu and 2 from Tonga, dating back nearly 3,000 years. This bone, tucked deep inside the skull, preserves DNA better than any other part of the body, especially in the hot, humid Pacific where genetic material usually vanishes. With just these 4 samples, the team managed to recover enough genome-wide data, about half the depth of a modern genome scan, to run robust ancestry tests. The results stunned the field. All 4 individuals showed over 99% of their DNA matching present-day people from Taiwan and the northern Philippines. Not a trace of Papuan ancestry appeared, not in the autosomal DNA, not in the mitochondrial lines, not even in the Y chromosome of the male. Every statistical model, from principal component analysis to admixture graphs, pointed to the same conclusion. The first Lapita settlers of remote Oceania were unmixed descendants of Austronesian voyagers, not a blended population shaped by earlier contact with Melanesian neighbors. This finding overturned generations of speculation. The Lapita Trail, once thought to zigzag through a corridor of cultural and genetic exchange, now looked like a bold leap, an express route from island Southeast Asia that bypassed the populations of New Guinea and the Solomons. The genetic signature was so pure that even the most sensitive tests could not detect more than a fraction of a percent of Papuan input. Only later, as new waves of contact swept eastward, would Papuan Y chromosome lineages enter the picture, a pattern that explains the modern 25% Papuan ancestry in Polynesian genomes. But in the bones of these first settlers, the story was clear. The architects of the Pacific's greatest migration came straight from Asia, carrying with them the language, crops, and navigational wisdom that would knit together the world's largest ocean. Alexander Ioannidis approached the Pacific's migration puzzle with a new tool: rare genetic variants, each one a marker left by the handful of voyagers who dared to settle a new island. Sequencing 430 genomes from 21 islands, his team tracked how these rare alleles faded and shifted, revealing a step-by-step path across the ocean. The journey's first clear genetic signature appears in Samoa, around 830 AD. About 120 years later, the Cook Islands show up on the genetic map, followed by the Society Islands, including Tahiti, by 1000 AD. The pace quickens from there. By 1100, the Tuamotu archipelago emerges as the launch pad for the last bold push east. Over the next 2 centuries, Polynesian navigators reach Easter Island, the Marquesas, and Raivavai, with each new settlement dated between 1100 and 1350, marked by a further drop in genetic diversity and a distinct founder effect. The Tuamotus become the key branch point. Genetic evidence ties the populations of Easter Island, the Marquesas, and Raivavai directly to the Tuamotus, linking them through a rare variant profile. This shared ancestry is mirrored in the statue-building traditions that spread with these voyagers, not as isolated bursts of creativity, but as cultural cargo carried across open water. The founder effect method lets researchers trace not just people, but the movement of ideas and identity. Ioannidis' work replaces vague migration arrows with a precise time-stamped route. Each island stands as a record of risk and ambition, each genetic fingerprint a reminder of families who crossed the world's widest ocean, leaving behind both their DNA and their stories. In 2020, a global team of scientists set out to test one of the most persistent legends in Pacific history. They assembled a dataset of 807 genomes, including people from 17 Polynesian islands and 15 indigenous American groups. The tool they used was identical by descent analysis, searching for long, uninterrupted stretches of DNA that can only be shared through a recent common ancestor. What they found was unmistakable. Polynesians from the Marquesas, Mangareva, and Rapanui shared 4 to 9 centimorgan segments with the Zenu people of Colombia. The dating, based on the length of these genetic tracks, pointed to a single episode of contact around 1200 AD with a margin of plus or minus a century. But the direction ran counter to Heyerdahl's famous drift. The gene flow moved westward, from Polynesian voyagers reaching the Americas, not the other way around. The genetic exchange was limited. There was no sign of mass migration or sweeping demographic change. It was a brief encounter, enough to explain the sweet potato's journey and to leave a faint but indelible mark in the DNA of both peoples. 15 ancient individuals buried on Rapa Nui between 1670 and 1950 have now given up their genetic secrets. Their DNA, drawn from dense petrous bone, reveals a story of continuity, not collapse. Across these centuries, the island's genetic diversity, measured by heterozygosity and the length of homozygous stretches, remains on par with other remote Polynesian communities. There is no sign of the catastrophic bottleneck that the old ecocide narrative demands. Instead, the genetic line runs unbroken from the original Lapita voyagers through the centuries of Moai building, European arrival, and the upheavals that followed. Ancestry persists, undiminished, through generations of Rapanui families. The evidence speaks not of ruin, but of resilience. A community that endured, adapted, and remained part of the wider Polynesian world. Today, every new genome sharpens the outline of a truth, once blurred by myth. Polynesian navigators crossed 1/3 of the planet by skill, not accident. Their story, written in DNA, defies limits. It reminds us that human ingenuity still leaves maps unfinished. What boundaries might we cross next?